Hello, thank you for attending our Advanced Wavelength Principles webinar. In this webinar, we will be focusing on non-visible wavelengths, such as IR and UV light. So when talking about the whole wavelength, we do want to mention the scattering rate. And what we're doing to measure the scattering rate is we have a sample, and we have a light source shining onto the sample, and then we have a detector that detects how much of that light is scattering and reaching the detector. And what happens is UV lights and blue lights, all lights with shorter wavelengths, have a very high scattering rate. So that light shines down, most of the light scatters away and goes to the detector or the camera. As we get longer and longer wavelengths, green, red, IR, that scattering rate decreases to even about 2.3 at 950 nanometers, but we get a much higher transmission rate. So what transmission rate is, it's where the light is actually going through the material and not reflecting off of it. So in colored materials, we can use IR light to make them more transparent and more colorless, and we can reveal more surface defects in that situation. But that is the difference between especially UV light and IR light, is the scattering rate will actually have a big component. So when talking about higher wavelengths, we're talking about near infrared light, or what we call NIR. And these wavelengths range from about 780 to about 1,000 nanometers. Typically in LEDs, you'll get a peak wavelength of about 850, 860, 940, 950, kind of within those ranges is your standard typical NIR wavelengths. This does not require a special camera. However, it must be a monochrome camera. And a lot of cameras have different spectral responses at different wavelengths. So if you do plan on using an IR light, it is a good thing just to confirm the spectral response of the camera you plan on using to make sure it has a decent response at that wavelength. So longer wavelength radiation is actually electromagnetic radiation, and therefore it oscillates less frequently than shorter wave radiation, and therefore it generates less interaction with materials, meaning that it's capable of penetrating deeper into the material and therefore generates fewer surface reflections and more of a short wave light, essentially saying it transmits instead of scatters. So when using IR light, it is even possible to look through an object. So that's one application example of transmitting through opaque materials that typically a standard visible light will not be able to do. We can also use it, as I mentioned before, as a surface inspection to remove print and see if there's any scratches, anything like that, where the text or the print on the object might cover that up. We've also been able to use it in combination with the filter to kind of remove ambient light or ambient daylight because of the higher wavelength. And a lot of times it is used because it is non-visible to humans, so it does not disturb operators. So as long as the IR light is not changing your image, it is a really nice solution to having a machine vision system next to operators without shining a bright red light in their face and causing them discomfort throughout the day. So an example of a high transmission application is looking at this bottle of soy sauce. With white light and that dark soy sauce, it's really hard to look through and see if there was foreign material inside of the bottle. Versus with the IR light, it can actually transmit through that soy sauce, shine completely through, have that light reach the camera, and then that foreign material in the bottom blocks it, so we can actually detect that foreign material in this bottle where visible light would not have been able to help us. Here's an example of removing the printing with that IR light shining through, transmitting through the text, making it appear colorless. It makes the whole background the same color, and we can see that pinhole, which was originally covered up by the dark seed of that apple. Another example is looking at perforation on a cardboard box. So that IR light is doing the same thing. It's penetrating through and removing all of that color to make it appear colorless. But I do want to touch on the fact that the red light actually creates a similar image. Now the red light is not transmitting through and appearing colorless, it's actually reflecting off. And because it is yellow and red, and like colors lighten, it's reflecting all of that light back at a similar rate, and therefore it's appearing very bright to the camera as well. So this is a situation where IR light and red light both provide a very similar image, and both would be considered a good solution. So CCS offers a large array of IR lights that are, ring lights, low-angle ring lights, bar, coaxial. So we offer this so people can optimize the collimation or optimize the bright field or dark field images with the reflections as well as the wavelength to create the best image possible. Ephilux also offers a wavelength of 850 nanometer versions of their lights, and you can get it in the flex, the ring, the backlight, and the flat dome light. So we've talked about high transmission examples. Here is a great example of a high scattering application. Here we have a cup that has scratches on the bottom. In the blue light shining down, you can sort of see the scratches, but it's not clear and would be hard to be reliable for the camera to inspect regularly. Versus if we use that UV light, we have a lot of contrast. And it's not necessarily that there is any fluorescence within that cup. There's no property that the scratching the cup gave it to fluoresce the material back. Really what's happening is that shorter wavelength is shining down, hitting the scratch where it's been disrupted and scattering that light back to the camera, and we're getting a lot more light with that higher scattering rate, so there's just a lot more contrast. But on the note of talking about UV light, I will go into what UV light is, what fluorescence is, and how we use it in machine vision. So UV light are wavelengths that range from about 365 standard, typical, to about 405 nanometers. It does not require a special camera, but I would again encourage you to check the spectral response of the camera you plan on using to make sure that it is high at shorter wavelengths. And it is used to excite certain materials during inspections, and we use it for applications to reveal invisible or UV ink or determine presence or absence of materials that fluoresce. This is typically some type of epoxy resin or a resin product, some type of inspection on a label, anything that might damp-proof insulated coatings, lubricant, things along those lines typically have UV properties within them. So I mentioned that it is used to excite material, but what does that mean? It's a very vague way to phrase it. Now I'm going to talk about what fluorescence is and what's happening to something that is fluorescing. So if you shine UV light onto a sample, there is a component within certain samples that have a phenomenon which can actually shift the light to a longer wavelength. So when that UV light shines down, the 365 nanometer shines down, hits the sample that has the property that can cause that phenomenon, the light that's reflected off the sample is actually longer. It's about 400 nanometers. So it gets changed and longer. And so now we have the 365 nanometer light shining down, and then the fluorescence 400 nanometer light going to the camera. So that's what the idea of fluorescence is, and when we look at lubricant on a gear, we can see that that lubricant is present because it's fluorescing, because it has that material or that property inside. So we can utilize that longer wavelength to create more contrast by using a UV cut filter. So what this UV cut filter is going to do is block out all of that shorter wavelength from that shined light, so all we see is the longer fluorescence light. And when you look at the application previously, by adding UV cut filter, we remove all of the light that is being reflected off of the gear. We're blocking all of that, so all we're seeing now is the light that is being fluoresced, and we're getting a very clear, very high contrast image that would be able to tell us if there's more or less lube, presence, absence of it, if it's in the right spot, wrong spot, etc. We can also use it to see that UV ink, as I mentioned. And these are typically the easiest applications because most time if a customer is using invisible ink, there will be some spec on the ink that says this fluoresces at this wavelength, and then you can just select a light that has that wavelength and you are all set. Other examples that are not as obvious and easy to do are things like glue. With the white light, it would be really hard to detect the presence or absence of that glue. With UV light and the fluorescing UV, we're able to see if the glue is there or not and if there's too much or too little. So one thing I do want to touch on is the difference between UV lights and UV curing. So CCS actually offers UV lights, and they now offer a UV curing line as well. So just to prevent confusion, I'll touch on what the difference is. So UV lights are for fluorescence applications. Just went through them: UV ink, presence, absence, gears of lubricants, glue. CCS, we offer 365 nanometer wavelength, and FELux offers 365 nanometers and 405 nanometers. The UV curing is different because what UV curing does is it uses ultraviolet radiant energy to chemically change a monomer or a liquid to a polymer, which is a solid. So it's used for adhering electronic components to one another, for printing onto CDs and DVDs, or creating harder coatings for plastic molded products. So by UV curing something, you're making the bond stronger, making it more sturdy. And CCS offers 365, 385, 395, and 405 nanometers. But really the difference between the two lights, even though the wavelengths are similar, is the amount of energy it takes. So UV curing light will require much more energy, much more power to do the curing process versus just your standard UV LED. So for standard UV LEDs, CCS has the UV3 line, which we actually just released. It's got ring lights, bar lights, spotlights, and line lights, and we're releasing a second line light very soon. So this is going to be brighter than the UV2 line we've previously had. FELux also offers UV lights. They offer in 365 nanometers and 405 nanometers, the FE Flex and the FE Sharp. And then the FE Line, FE Ring, FE Smart, and version 2 of the FE Sharp are offered in 405 nanometers. The FELux line also has a really cool technology called the pure UV technology. So 9 out of 10 times, a standard UV light shining on a sample is going to work very well, but every once in a while you get a sample that just has a lot of glare that's really hard to remove. So you can see the image on the bottom left. With a 365 nanometer bar light shining on a very reflective sample, there is a lot of glare that's covering up that date code. If I move to the next image and add a UV cut filter, it improves the image, but you can still see some of that glare, and that's just kind of a standard issue for highly reflective parts with UV light. But if I step over to the pure UV technology, which has an optical system inside that improves the excitation and removes the glare, in combination with my UV cut filter, I have a higher contrast image with absolutely no glare. So this is perfect if you have highly reflective samples and you're trying to do UV and you're just not getting a very consistent image. So that's it for talking about UV light and NIR light. So now I want to touch on just a little bit the SWIR light, which is shortwave infrared lighting. I'm not going to go in depth just for the sake of time, but I'll touch on it a little bit just to kind of pique your interest. So what is SWIR light? It is actually the spectral band between 1,000 and 2,500 nanometers. It requires a SWIR camera, SWIR lights, and sort of a SWIR lens. It's not actually required. It'll just get you a better image if you do use a SWIR lens. And as I said, it stands for shortwave infrared light. So very quick, what do we use SWIR light to do? We use it to differentiate between two materials. It can actually make water appear very dark based on the properties of the SWIR light in the water. So you can get presence absence of moisture on metal before it goes to the next part of your process, looking at fill levels of typically clear material. It can reveal something hidden. We can look at it on wafers, and it can reveal the layers within what it looks like in between the layers of the wafer. And then you can use it to see through product that you typically can't see through, even more than NIR can. Usually it's plastic or silicone, but every plastic is chemically different, so it is impossible for us to know ahead of time which wavelength will work on what plastic. It really does require testing. We do have a SWIR lab in our Boston office, so if you think you have an application that SWIR will be effective on, please reach out and we can work on testing that for you. But that is all I have for the presentation portion, and I will now hand it over to Austin to complete our lab portion for this final webinar. Thanks.
Hello, welcome to the lab portion of today's webinar. I'll be showing you a hands-on application using ultraviolet and near-infrared lighting. I have a few samples, one's right there, and I'll be showing you the others later today. All these samples can be found at Target or Stop and Shop. They're everyday items. So let's get started with this one. So we have a cornstarch Argos container, and we would want to do a fill line inspection. So we'll start with the white backlight we have right here. And that is way too bright. Let's turn that down. If we get closer, you can't really see the fill line. That is being covered up completely by the label. And if I turn off the lighting, of the room lighting, that's not going to get any better. So let's switch over to the IR 950 nanometer wavelengths and give this a try. It did get better. So, yes, it got better. You can see it, but it can still be improved. The room lighting is interfering with the completely seeing through. They're seeing the lighting hitting the front and going to the camera. So, that is an IR cut filter. Only IR wavelengths can go through, or we could turn off the room lights. It's the same thing, almost the same thing, and that is a lot better. We can adjust the lighting if we want to, but right there should greatly help. If we wanted to even make this a better application, we would be trying to do this inspection without that label there. And that would solve all issues. It can be seen clear as day right there. And let me now get started with the next application. The next sample we have today is a pure vanilla extract, and it's going to be also like the last one. It's going to be a fill line inspection. So we're going to try the white light again. I did decrease the size of the white light for this one. There wasn't any reason to go as big as the last one. And let's just reduce that. So, very hard to see. And if we turn off the light, it'll still be pretty much the same exact image. So, let's swap this out with the NIR. And this is what you get. If we move it, you can see it pretty well. Now we have the IR cut filter. Not really much of a difference. So now the true test. We grab the same exact model with a different fill line. And you can clearly see it. Not much with the IR cut filter on this one. So, clear as day, you can see where the fill line, if it's below that ridge. It'll be a little difficult when it is at that top level. There it is. It'll be a little difficult if it's at that top level right there. So we'll do a white background as a comparison. It can work, but it's still really hard to see. That's better. Still a little difficult even when you get further up. Clearly the IR is better in this case, especially if it gets to that level right up there. But that's the second one. Let's move on to our third application. So for our next sample, we have a box of Claritin. And the main objective is to inspect the back end, see if there's any defects in the text. So when we put it in the camera, we're going to first use the white light, and we're going to see if we can see the defects. Now, none of the defects, there's 3 of them, and it's very hard to see. Nothing immediately stands out. So we're going to use the IR dome light, flat dome light that we have. It is 850 nanometers. So we're going to put that over. And the reason why I wanted to show this one was because at the wavelength 850 nanometers, there is still texture. So we would need to go higher. And I would mess with this a little bit more, but the defect still cannot really be seen from this. So we're going to move on to the backlight again of the 950 nanometers. We're going to use a RIR cut filter, put that in, and immediately we can spot 3 defects. So the first one is right over here, it's a puncture. The second one is right here, also a puncture. And this is a scrape. And that might be a puncture, it might not. But it is still clearly a defect. And when we remove it, just try and do this correctly. You should be able to see it is right over the text, which would make it really hard for a normal light to see. So that's one very good use of the near infrared wavelength. And for another one, what we have is a chapstick, Blistex. So we're just gonna put that right there. We're gonna focus this thing really quick. That's pretty good. Move those over and this to the center more. Doesn't have to be perfect. We're not inspecting the words on this one. All we're doing is inspecting the cap. So this will just be a cap inspection. And we will first use the white backlight and just try and see through this. Unfortunately, even if we change the working distance, a white light just does not go through the cap of this Blistex at all. Meanwhile, let's put that back. As you can see, we have a clear inspection right there. We'll see if this helps. Does a little bit. And we can optimize this even more by making it a shorter emitting surface, as well as adjusting the working distance, find the best one. But that will be our cap inspection, and I'll get the other one set up right now. Alright, so we have our Scotch restickable mounting dots, and what we're going to want to do is, for this type of inspection, we will want to clearly see the dots. We want to know they're in there. So what you're seeing now is 2 of them stacked on top of each other. the way it is right now, it's not flushed in the industry. When it's manufacturing, it's going to be laying on a conveyor belt and they're going to be neatly stacked on top of each other. But for this application, we're not going to worry too much about that at the moment. We want to be able to clearly pick the dots from the background, and there's a lot of noise going on in the background with all the diagonal lines and the patches. So let's see what we can do. So we're going to first try the white backlight. And we're going to there we go. Unfortunately, not really much of a contrast at all. So let's try the IR. With the IR light, we have, unfortunately, the same issue. Even if we had the cut filter, it's not going to get any better than that. So, backlights are going to have a hard time on this one. When we use the white one and put it towards the front, at the right angles, maybe it's still going to be really hard with the stripes, very hard, and there might be a way that I'm just not seeing at the moment, but there's definitely an easier way, and that is with UV light. So we're going to see if that's fluorescent, but first I just got to put on my UV protection glasses. Grab the UV light and point that away from me. And what we see that they are fluorescent. And what you also see is a glare. What I put on is a UV cut filter. So that glare may be an issue. We gotta spin it just right to remove the glare. But it is definitely a type of wavelength we would want to consider for inspection. Now, say we did want to put it like this. And even the UV cut filter can't reduce that stripe that's going down. What we also have is the pure UV. And the main purpose of this is to make sure there's no glare. So it is bigger, but there we go. Sorry about that. The glare is gone. So that definitely allows us to put it with the areas we would really want the light to be in, that the regular UV lights it won't work. So it's a great thing about the pure UV. And now we're going to go into our other UV applications. Alright, so for our next application we have a Febreze bottle. And what we're going to be doing with this is there's an inspection that can be done on the seam. And I'll just put this there. Make sure it's completely focused. And we'll turn it to the back. And what we're inspecting is this seam. So, you probably already know this is the UV application, but we'll go through the motions of using the backlights we've been using. And we can truly see the difference. So, really quick, here is the white light. Very white. And there's really no indication you can see other than a thin black line that would mark one of the edges of the seal. So unfortunately a white light isn't going to work on this. Moving to the IR, what we have here, it's going to be close to the same issue. And if I wanted to, I can add the IR cut filter, and I'm not really going to see much about trying to bring out that seal. Fun fact with this, so if we did want to do a fill line inspection on this, it is able to see that fill line pretty well, but we're not doing that for this application. So next we finally bring out the UV light. We're going to use the same UV bar light that we did before. It's a little bigger, but should do the job if this is a UV application. UV protection glasses, and we also have the light pointed away. You don't want to point it towards your eyes. And what we can do is see that it does light up. We can then add a UV cut filter, and we can see that line pretty well. We can see the seal. Depending on the background, it may get a little confusing. I am noticing that there is still a glare coming from the UV light. That glare, you can find the ideal solution around it to prevent that glare. It may become more of a sensitive type of inspection where the bottle has to be a certain way. Or we could go back to the pure UV, and this is a little smaller than the sample itself, so we may, if this works, we may want to consider going to bigger size. So let's plug this in and keep that cord away from me. Alright, and what you just saw in the beginning was the overdrive feature. As you can see, there won't be any issues with the glare. This is very flexible, and we can get the light where we want it to be, where it will be convenient for us, and as well as working with our system. Now what we can do is really overdrive this, and we can really see that line. So the strobing causes the overdrive to kick in, and if this was a even bigger light to completely fit this this type of sample, it would come out really well. So what we have also is this one, where it's also the same type of seal inspection as going down this. It is finished jet dry rinse aid. So we'll put that in. We'll try and quickly focus in here. And what that seal is about over here. Alright, sorry about it taking a little while. Just to make sure it's completely focused in. Looks pretty good to me. It's a little dark, but that's because there's no light being shined on it yet. So we're going to stick with this one. The pure UV is going to do the job. and start strobing now. So right over there, as you can see, very clear as day type of application, and we can make it even better by doing that. So really simple, easy application we can do on this. And these lights will definitely work with this type of inspection. So I'll get the next sample set up and I'll see you in a minute. Alright, so for our final application today we have Pringles. And we have a UV code that is hidden right over there. And we're just going to use a UV light and find the code and show that it is there. Let's focus in. Alright. And we're going to stick with the UV pure light. It's been working pretty well for us. And we're going to angle it right up at the UV print. So let's just go there. UV glasses and never look at the light. That is the overdrive. There is the print. So we can definitely make this a little bit better. One way, UV cup filter. And we can close the aperture. And there we go. Very short, very easy, and very simple.